Hi, we're group 4, and my name is Shamiso.
I'm Sultana.
Adriana.
Carolina.
Bye. Once upon a time, in this disputed area in 1836, we had a bunch of hungry people. We are hungry. What to do? So they saw a bunch of animals and decided, ooh, let's make bow and arrows. We'll get food. So the solution, potential energy in the bow and arrow. And so they hunted the animals with those bow and arrows. How the bow and arrow works. Potential energy is greater than kinetic energy before the arrow is pulled in the system. The potential energy in this case is greater still than the kinetic energy because the arrow hasn't started to move. And this is the least stable position because it's being pulled and all this potential energy is being accumulated in the system. In this case, the potential energy is less than or equal to the kinetic energy because the bow is released, the arrow is released from the bow and begins to move, therefore there's more kinetic energy. In this case, the arrow is freely going, and the potential energy is less than the kinetic energy to the point where it will stop. And this is the most stable position because the kinetic energy is greater than the potential energy. The graphs for this look like this. At this case, the arrow hasn't been pulled away from the bow, so this is where the potential energy lies. It's fairly stable. In this case, the potential energy is very high because the bow and arrow are in a position where the arrow needs to go away from the bow. In this situation, the potential energy is lower than it was before, but is decreasing because the arrow is going away from the bow. And then finally, in this position, the energy in total, the potential energy increases, and the kinetic energy also increases, but the kinetic energy is higher than the potential energy, and therefore it lies over here. And as the potential energy decreases, the kinetic energy increases. The end.
Learn about fluorine. So in the neutral fluorine, there's a positive 9 charge in the middle, 2 electrons in the first shell, and then 7 electrons in the outer shell. In fluorine negative, there's a positive charge in the middle, 2 electrons in the first shell, and 8 electrons in the outer shell. In the first shell, the electrons feel a positive 9 charge. In the outer shell, they feel a positive 7 charge. In fluorine positive, there's a positive 9 charge in the middle, 2 electrons in the first shell, and 6 electrons in the outer shell. Fluorine has the least amount of potential energy because there is no charge. Fluorine negative has the most potential energy because of the repulsion. Positive fluorine has more potential energy than neutral fluorine because there is a positive charge leaking out but only 6 electrons in the shell. Here is a diagram of the potential energy where fluorine has the most, and then positive fluorine has more potential energy than neutral fluorine.
Hello, I'm going to be talking about the molecular potential energy in CH2F, CH2CH3. When this is the structure, and then I put it in Newman projection, when the fluorine and CH3 in 0 degrees, it is most potential energy because it's unstable, because these two molecules are attracting each other, are repelling each other. When CH3 and fluorine is in 60-degree angle, it is a little bit less repulsion, so it is less potential energy than the 0 degree. When CH3 and fluorine is in 120 degrees, there's still some repulsion, but it's not as much as the 0 degree. When CH3 and fluorine is 180 degrees, it is less potential energy because there's less repulsion going on. There's on the two and this is the diagram for the potential energy and the degrees. In 0 degree, potential energy is the highest. In 60, it's low but not yet completely less stable, not completely stable. In 120, it's still high in potential energy but not as much as high as 0 degree. In 180, the molecule is completely in stable stage.
Okay, so here I'll be explaining the potential energy between these two reactants in our reaction. First, we have a partial negative charge on this nitrogen that makes it unstable. And then we have a partial positive charge on this hydrogen and a partial negative charge on the oxygen. We have these electrons on the nitrogen that are attracted to the partial positive charge on the hydrogen and therefore are going to pull it closer towards the nitrogen. This is the first step in our reaction. So as we move over here, we can see that the oxygen becomes more negative since it's gaining the electrons from the hydrogen, whereas the hydrogen is pulled towards the nitrogen, and the lone pairs will be in this bond here. So now we move towards the reaction between the two reactants, and we look for a high electron transfer potential. So in this oxygen, we have a partial negative charge, or actually no, we have a complete negative charge. And then on our other reactant, we look for a positive charge that will attract that negative charge. So the nitrogen is most electronegative and will make this carbon our most positive. So the electrons from this oxygen will pull this carbon, but then our carbon, which already has two hydrogens bonded to it, will have too many electrons, forcing this bromine to pull its electrons closer to its shell. Here we show our transition state, where you can see the electron cloud from the bromine move closer towards the bromine, getting rid of this bond between the bromine and the carbon, and creating a bond between the carbon and the oxygen. So then in our final step, over here we see that the carbon has created a bond with the oxygen, and then the bromine comes off as a negative charge, which is more stable than the negative charge that we had on the nitrogen initially. This will be an exothermic process, as you can see, where there's a difference in energy from start to finish, and at the peak will be our transition state.
Hello, so this is another route in our maze where the nitrogen will be attracted to the positive of this carbon. This carbon is positive because the electron density is more found closer to the bromine. So when the nitrogen attacks the positive charge, our product then looks like this, where the nitrogen has made a bond, is making a bond with the carbon, as well as the bromine coming off and taking its two electrons, the two electrons from this carbon, well, one electron from the carbon and one of its own, and therefore we end up with this final product and the bromine with a negative charge. This is our minor product from a whole reaction, but our major product is the one we previously showed you, which looks like this. plus the bromine with a negative charge. This is our major product. Over here we have our potential energy graph of both the minor and the major products. In this case, they both lose energy, so it's an exothermic reaction for both products. However, our major product has got a smaller activation energy. Henceforth, that's why it's our major product and it's more produced because there's a smaller activation energy needed to have the reaction to go through.
Thank you for watching our video. Keep lowering your potential energy.